Across the barren lands of prehistoric Australia, hidden beneath the dust of time, there once existed a creature weighing nearly half a ton, moving like a living machine with a beak powerful enough to crush bone itself, Dromornis. It appeared only near the very end of that long-forgotten history, like the final remnant of a dying age. Because long before its arrival, through millions of years of isolation, this land had evolved into a world completely separated from the rest of the planet, operating according to its own rules. And prehistoric Australia did not end with Dromornis. This isolated continent once gave rise to creatures far more terrifying than even that colossal beast. Around 45 million years ago, Australia had not yet fully separated from the supercontinent Gondwana, a landmass once connected to Antarctica, South America, and Africa across an Earth filled with ancient rainforests and interconnected ecosystems. But as slow tectonic movements began, Australia gradually broke away from Antarctica, drifting northward at a rate of only a few centimeters per year. It seemed insignificant, yet across tens of millions of years, it was enough to transform an entire continent into a world completely cut off from the rest of life. As the ocean currents surrounding Antarctica formed, Antarctica became locked in ice, while Australia drifted into increasingly dry climate zones across the planet. The ancient rainforests that once covered the continent slowly disappeared, replaced by sparse grasslands, scrublands, and deserts that expanded without end. Australia was forced to function as a closed system for tens of millions of years, following an entirely separate evolutionary path where marsupials became the center of the entire ecosystem. They did not merely survive. They occupied nearly every ecological role filled elsewhere by placental mammals, giving rise to forms of life that seemed both strangely familiar and completely alien. Some resembled lions, yet were actually marsupials. Others looked like giant rodents weighing hundreds of kilograms. Even kangaroos evolved into upright, two-legged walkers rather than relying solely on hopping as they do today. In that world, creatures like Dromornis were no longer abnormalities, but part of a larger pattern of extreme evolution, where every ecological vacancy was filled by bizarre life forms, sometimes more terrifying than anything imagination could invent. One example was Thylacoleo carnifex, the marsupial lion, an apex predator with one of the most powerful bite forces ever measured among mammals, despite evolving from herbivorous ancestors. Another was Diprotodon, the largest marsupial ever discovered, stretching nearly 4 meters long and weighing more than 2 tons, resembling an impossible hybrid between a wombat, a hippopotamus, and a rhinoceros while belonging to none of those familiar groups. The true horror was not any single creature, but the entire ecosystem itself, isolated for more than 30 million years with no outside competition, no incoming migrations, only the relentless pressure of survival inside an arid, unstable, and unforgiving environment. And under those conditions, evolution did not create perfection. It only created forms that were sufficient to survive. But in Australia, sufficient to survive took on a very different shape. Creatures capable of crushing bone, enduring prolonged starvation, conserving every drop of water, and adapting to a world that was always ready to transform into something even more extreme. To understand why Australia produced such brutal monsters, we have to look beneath its surface. If there was an invisible force that shaped all of prehistoric Australia, it was not only biological isolation, but fire itself, combined with a foundation of soil so nutrient-poor that it bordered on extreme. Australian soil suffered from severe phosphate and nitrate deficiencies, and many geochemical studies suggest that nutrient levels here were significantly lower than those found across temperate continents, forcing plant life into a near-constant state of maximum energy conservation at the most fundamental biological level. It was on this impoverished ground that ancient eucalyptus forests emerged, carrying oil concentrations that could range from roughly 5% to more than 15% of leaf mass in certain species. Levels of microcharcoal increased significantly, suggesting that fires not only became more frequent, but also spread across far larger regions. Without massive herbivores regulating vegetation, fire gradually became the dominant controlling force of the ecosystem. But the astonishing reality was that fire in Australia became more than destruction. It evolved into one of the forces that shaped life itself. Many plant species adapted directly to recurring fire cycles. Others evolved in the opposite direction. Their seeds would only germinate after experiencing the thermal shock of intense heat. Fire became a kind of biological switch, triggering the regeneration of entire ecosystems. Herbivores were forced to adapt to landscapes that were constantly being rebuilt, moving through recently burned terrain to feed on fresh vegetation. Predators learned to exploit the chaos left behind by fires, hunting prey concentrated into the few surviving patches of habitat. And within that entire system, the most dangerous force was not any predator, but the environment itself. Under those harsh conditions, marsupials became the dominant form of life. They evolved toward flexibility and extreme energy efficiency. Many species could regulate their reproductive cycles according to environmental conditions, even delaying or reabsorbing embryos during periods of drought or food scarcity. Creatures considered primitive in other ecosystems became, in Australia, the life forms best suited for survival in extreme conditions. And when adaptation was pushed to its limit, Australia witnessed the rise of giant marsupials. Diprotodon, the largest marsupial ever known, weighed nearly 2.7 tons and moved in herds across vast arid landscapes. Procoptodon, the giant short-faced kangaroo, stood taller than a human, with a body structure designed for efficient movement across open terrain. Palerchestes, a bizarre creature resembling a fusion of multiple animal groups, developed highly specialized adaptations for feeding on tough, dry vegetation. But inside an ecosystem already inhabited by multi-ton animals, what could possibly control them? Thylacoleo carnifex, the marsupial lion, emerged as an apex predator with one of the strongest bite forces relative to body size among mammals, equipped with razor-sharp claws and ambush strategies launched from above. It was the product of an entirely different evolutionary pathway, where a lineage of herbivorous animals had been twisted into the ultimate predator. From that point forward, Australia became an ecosystem where fire, nutrient-poor soil, and extreme evolution combined to create a world trapped in a constant state of survival tension, where every creature, whether herbivore or carnivore, was forced to operate at its absolute biological limit, simply to survive through one more dry season. But when thirst began to suffocate life itself, every herbivore was forced to gather around the few remaining sources of water. And when we look at prehistoric Australia, one survival design stands out above all others: the marsupials. They were not simply another group of animals, but an evolutionary strategy completely separate from the placental mammals dominating the rest of Earth. How do you sustain life in an environment where water can disappear within weeks, food availability changes through extreme seasonal cycles, and droughts can last for months at a time? In Africa or Eurasia, placental mammals such as elephants, horses, and lions invest enormous amounts of energy into each reproductive cycle. But in an unstable environment like prehistoric Australia, a single unexpected drought could easily mean death for both mother and offspring. And marsupials emerged as evolution's completely different solution. Instead of carrying the pregnancy for a long time, marsupials give birth to premature babies at an extremely early stage, sometimes only a few centimeters long, with almost no fully developed organs. The hatchling immediately crawls into its mother's pouch, a kind of mobile survival chamber, where it continues to develop in a more stable environment. In the red kangaroo, Macropus rufus, newborns weigh only a few grams at birth, yet inside the pouch they can continue developing gradually according to the changing conditions of the outside world. What is even more remarkable is that this system is not simply a method of raising young. It functions as a real-time biological regulation mechanism. Many marsupial species can temporarily pause embryonic development when environmental conditions become unfavorable, especially during periods of water or food scarcity. Once conditions improve, development resumes. This is an extraordinarily rare form of reproductive coordination in the animal kingdom, allowing them to avoid wasting resources on offspring unlikely to survive. From an evolutionary perspective, this became a survival-first reproduction strategy. Reproduction that prioritizes survival potential over sheer numbers. Instead of maximizing the number of offspring, marsupials optimized their ability to wait for the right moment to reproduce. On an arid continent where resources fluctuated violently and unpredictably, this became an overwhelming advantage. It was this relentless environmental pressure that allowed marsupials to dominate nearly every ecological role across Australia. With no competition from placental mammals, they began expanding into every biological niche: herbivores, burrowers, scavengers, and apex predators. Some species resembled lions, yet belonged to marsupial lineages. Others looked like gigantic rodents, weighing hundreds of kilograms. Certain kangaroos evolved into upright, two-legged walkers with massively built bodies, no longer resembling the familiar image of bouncing animals we know today. And there were even creatures shaped like rhinoceroses or hippopotamuses, despite belonging to entirely separate evolutionary branches. Weighing nearly 4 tons, standing over 1.8 meters tall at the shoulder, and reaching roughly 2.5 to nearly 3.5 tons in mass, it rivaled a modern rhinoceros or even a small truck in size. But what made Diprotodon remarkable was that it was not a predator. It was a herbivore, moving slowly across arid plains while crushing tough, silica-rich vegetation, plants that most modern animals would struggle to digest efficiently. The structure of its teeth reveals extreme levels of wear, perfectly consistent with a diet built around dry, nutrient-poor plants that dominated the landscapes of ancient Australia. But its peaceful appearance was deceptive. If cornered, the structure of its rear jaw could generate bite forces reaching nearly 11,000 newtons. In practical terms, it could crush a human femur as easily as snapping a cracker in half. When viewed in the context of prehistoric Australia, the age of giant marsupials was not simply a phase of increasing body size. It represented an extreme leap taken by an entire ecosystem, a world where life itself was pushed toward its physical limits. Then came Purest, one of the strangest creatures in this entire ecosystem. Early scientists initially mistook it for a relative of the tapir because of its elongated skull structure and enlarged nasal bones, features suggesting the possible presence of a small elephant-like trunk. But in reality, Purest was a leaf-eating marsupial that evolved along a completely separate path, using its specialized head and jaw structure to pull, tear, and process vegetation within ancient open forests. It was an independent evolutionary solution to the exact same survival problem. But if an ecosystem contained creatures weighing as much as 3 to 4 tons, what could possibly control them? It was a marsupial monster, Thylacoleo carnifex. This marsupial lion possessed an astonishing evolutionary paradox. Its brain was remarkably small, an inherited trait from its distant relatives, the koalas. Yet that smaller brain created additional space within the skull, allowing massive jaw muscles to anchor themselves with extraordinary density. The result was something almost impossible. Pound for pound, Thylacoleo possessed the strongest bite force ever recorded among mammals, comparable to an African lion weighing nearly 2.5 times more than it did. Instead of long canine teeth, it evolved protruding incisors shaped like sharpened chisels and premolars flattened into dagger-like blades. It could bring down prey up to 15 times its own size in less than a minute by severing the trachea and major neck arteries. Fossil evidence suggests it could conceal itself in trees or elevated terrain before launching downward attacks from above. An extraordinarily effective ambush strategy within the open and arid landscapes of prehistoric Australia. Some claw marks and cave fossils also suggest that it dragged carcasses into sheltered areas to feed over time, meaning it did not merely kill prey, it controlled the entire hunting space around it. And perhaps the most terrifying fact of all is that Thylacoleo did not evolve from a traditional lineage of carnivorous mammals. It originated from a branch of herbivorous marsupials. In evolutionary biology, this is an extreme form of evolutionary repurposing, when an original structure serving a basic survival function is repurposed to create an entirely new function. No matter how terrifying carnivorous mammals became, they still bowed before the cold-blooded horrors that ruled this continent. In Australia, the age of reptiles never truly ended. Look at Quincana, a crocodile reaching lengths of up to 6 meters, yet it did not wait silently beneath the water. Its long, upright legs and hoof-like toes allowed it to lift its body high above the ground and sprint with remarkable agility through open woodlands. It hunted by pursuit, charging after prey and delivering devastating bites that tore away massive chunks of flesh, causing victims to bleed to death without ever needing to drag them underwater. Fossil estimates suggest it measured roughly 3 to 5 meters in length, and instead of simply waiting for prey near water, it could actively pursue animals through ancient woodlands and grasslands. Alongside it existed Wanambi, a giant primitive python stretching approximately 6 to 8 meters long. But what made it terrifying was not its size. It was its hunting strategy. Based on the structure of its skull and jaws, Wanambi likely could not swallow extremely large prey whole the way many modern pythons can. Instead, it constricted and tore apart prey piece by piece. This was a low-energy but extraordinarily efficient predatory system for arid environments where every attack needed to maximize the energy gained in return. Then came Megalania, also known as Varanus priscus, the largest monitor lizard ever to exist in Earth's history. Fossil analyses suggest it may have reached lengths between 5.5 and nearly 7 meters while weighing more than 500 kilograms, making it one of the largest terrestrial predatory reptiles ever known. Some studies even propose that it may have possessed venom glands similar to those of the modern Komodo dragon, meaning its bite may not only have inflicted mechanical damage, but also gradually weakened prey through venom and infection. They were not designed for prolonged high-speed chases like cheetahs. Instead, they specialized in ambushes, inflicting injuries and exhausting prey over time. If there was one place where the entire ecosystem of prehistoric Australia converged, it was not around a single species, but around water itself. And yet the paradox was this: water here was not only life, it was also a trap. On a continent where rainfall in many regions remained below roughly 250 millimeters per year, and where some periods passed for weeks or even months without rain, every creature was forced to move toward the few remaining water sources. But that convergence created a brutal ecological paradox. The more desperately life depended on water, the more everything was drawn into the same location. Imagine a waterhole deep within the ancient outback. Surrounding it are the tracks of giant creatures like Diprotodon weighing nearly 4 tons, herds of Procoptodons standing over 2 meters tall moving slowly across the landscape. But when all life converged, the entire food chain converged with it, transforming the area into an extreme biological hotspot. There, predators no longer need to search for prey. The prey comes to them. Quincana could conceal itself within dry mud or thick brush, waiting for the perfect explosive moment. Even marsupial predators, like Thylacoleo, could use elevated ground to oversee the entire survival arena below, selecting the exact moment to strike. But what made the waterhole truly terrifying was not merely the presence of predators. It was the environment itself transforming into a system that supported death. As droughts intensified, water quality deteriorated rapidly. Minerals became increasingly concentrated. Decaying animal carcasses fueled bacterial growth. And in some cases, localized toxic anaerobic mud zones may have formed. At the same time, wildfires could begin closing in around the area. Geological evidence suggests prehistoric Australia experienced massive fire cycles, with flames spreading across hundreds of kilometers under dry heat, and through oil-rich vegetation such as ancient eucalyptus forests. The result trapped the waterhole between two extremes, dwindling water on one side, advancing fire on the other, turning the entire region into a sealed survival pressure system. Ecologists describe this phenomenon as water stress ecology, the ecology of water pressure. But in prehistoric Australia, it became more than pressure. It became the organizing principle of the entire ecosystem. Every food chain, from giant herbivores to reptilian predators, was drawn toward the same location at the same time, creating maximum biological interaction density. And within a system like that, death was no longer random. It became a law of probability. The closer something moved toward water, the greater the risk became, until life and death were separated by only a single step. And when we step back to view the entire picture, a deeper truth emerges. In prehistoric Australia, the waterhole was not a place of salvation. It was a survival filter. And within that system, nature did not need to hunt. And here it is, the peak of prehistoric terror, the creature standing at the top of Australia's terrestrial food chain, Megalania. The ultimate weapon of Megalania was not its muscles, but the venom glands hidden within its lower jaw. Its venom contained extremely powerful anticoagulants. Megalania only needed to ambush its prey, deliver a single bite, and then retreat. The wound would continue bleeding uncontrollably, leading to falling blood pressure, infection, and systemic shock. This 2-ton giant killer simply had to crawl slowly behind the fading shadow of its collapsing prey, waiting for the inevitable death to arrive. Then, around 65,000 years ago, an entirely new variable appeared across the ancient continent of Sahul, the ancestors of humanity. And what mattered was not that humans were physically stronger or faster than the predators already ruling this land. It was that they carried something this ecosystem had never faced before: intelligence combined with the deliberate use of fire. But that very smallness concealed an entirely different survival strategy: changing the environment instead of merely adapting to it. As humans spread across Australia, they introduced a tool no species before them had ever used at an ecosystem-wide scale: fire, stick farming, the deliberate and controlled burning of landscapes. Archaeological studies suggest that within only a few thousand years after humans arrived, vegetation patterns had already shifted dramatically across enormous regions. Dense forests transformed into open savannas. Fire cycles became shorter and more frequent. Species that had remained stable throughout more than 2 million years of the Pleistocene disappeared within roughly 10,000 to 20,000 years, a mere blink compared to evolutionary history. They did not vanish because they had suddenly become weaker. They vanished because the equilibrium system sustaining them was disrupted simultaneously by climate shifts, fire, and human activity. As the megafauna disappeared, the ecosystem itself began to reorganize. Plant life shifted toward species better adapted to drought, but also far more flammable. Wildfires became increasingly frequent and more intense, producing vast, dry landscapes across the continent. This is what ecologists describe as an ecosystem cascade, a chain reaction in which the disappearance of one group of organisms triggers structural transformation throughout the entire ecological system. Australia, in this sense, was no longer the same ecosystem. It had become a new version rebuilt through absence. From that moment forward, the continent entered a new state, one in which humans were no longer simply part of the ecosystem, but had become the force reshaping the entire system itself. If we look at the entire story of extinction in ancient Australia, the first thing to understand is that it was never simply about a few species disappearing. In reality, it was a continental-scale restructuring of the entire ecosystem. During the late Pleistocene, roughly between 50,000 and 20,000 years ago, Fossil evidence suggests that more than 85% of Australia's large animals weighing over 44 kilograms vanished within a relatively short geological period. And, most importantly, the first major impact did not occur among animals, but within plant systems. When mega-herbivores like Diprotodon, weighing roughly 2.5 to 3.5 tons, disappeared, the continent also lost its natural biomass consumption system. This marked the beginning of a chain reaction that would eventually reshape the entire continent. Data extracted from ancient charcoal sediment cores reveals a major shift in wildfire frequency following the disappearance of the megafauna. Levels of microcharcoal increased significantly, suggesting that fires not only became more frequent, but also spread across far larger regions. Without massive herbivores regulating vegetation, fire gradually became the dominant controlling force of the ecosystem. The next effect emerged as a long-term accumulation of smaller climate reactions. As vegetation cover declined and wildfires intensified, soils lost much of their ability to retain water and organic carbon. This process represents what ecologists describe as an ecosystem feedback loop, a self-amplifying cycle in which the disappearance of living organisms triggers physical environmental changes, and those altered environments continue limiting the ability of life to recover. What makes this process especially remarkable is that it did not produce an immediate collapse, but rather a phased transition. The ecosystem did not die, it shifted into a different state. Simpler, drier, and containing far less biomass. Over longer timescales, this suggests that modern Australia may not be a completely separate ecosystem at all, but rather the surviving version left behind after a massive ecological decline. The highly flammable eucalyptus forests, the vast semi-arid regions, and the dominance of species adapted to extreme drought all carry traces of a world that may once have been far more biologically complex. And when all of these pieces are viewed together, the most striking reality is not simply that species disappeared, but the way their disappearance propagated through every level of the ecosystem, from animals to plants to fire to climate itself. A complete ecological domino effect where every collapsing link forced the restructuring of the entire system. And in the end, what makes this story truly unsettling is not the past that was lost, but the principle hidden beneath it. In nature, extinction is not an ending. It is a variable capable of rewriting the structure of an entire planet in ways that unfold slowly, yet become impossible to reverse. This journey back through time has revealed a magnificent, yet deeply brutal chapter in the history of prehistoric Australia. Across tens of millions of years of near-total isolation, evolution on this continent diverged into an extreme direction, producing gigantic creatures equipped with some of the most extraordinary biological structures and natural weapons ever seen on Earth. The most dangerous land in history did not end merely with the extinction of a generation of creatures, but with a powerful scientific reminder of the limits of survival itself. In nature, no matter how perfect adaptation may seem, it will always remain vulnerable to the larger forces capable of reshaping an entire planet. In the middle of a dense forest, the air is warm and humid, carrying the scent of wet soil. Sunlight filters through towering canopies, reflecting across the still surfaces of ancient swamps. Insects buzz in the air, vegetation grows thick and crowded, and beneath your feet lies soft earth, soil that today is buried beneath kilometers of ice. The ground trembles slightly as heavy footsteps draw closer. The treetops sway gently, the birds fall silent, and from the damp mist, a colossal creature emerges, several meters long and weighing tons. It moves slowly through the forest. This is the domain of dinosaurs. The presence of dinosaurs in Antarctica has been confirmed through fossils discovered in the Transantarctic Mountains and in several other regions. Fragments of bone, tooth marks, and skeletal structures all indicate that between roughly 190 and 70 million years ago, life here existed on a large, complex, and stable scale. One notable species is Glacialosaurus hammeri. This plant-eating dinosaur belongs to the sauropodomorph group and was identified from fossils discovered in Antarctica. Based on skeletal analysis, it measured about 6 meters in length and may have weighed several tons, comparable to a modern Asian elephant. But another remarkable feature lies in the structure of its limbs and hips, which suggests it was not a slow and solitary creature. This matches the environment of ancient Antarctica perfectly, where rivers and swamps dominated the landscape. Where patterns on its teeth indicate a diet of tough vegetation, possibly conifer leaves or young plant stems, abundant food sources in this forest ecosystem. Did it live alone or move in herds? While there is no direct evidence of herd behavior from Antarctica itself, comparisons with similar sauropodomorph species in South America and Africa, regions once connected to Antarctica within the supercontinent Gondwana, suggest that these animals likely moved in groups. This leads to an important conclusion. Antarctica was not merely a place dinosaurs passed through. It was a place where they lived for long periods of time. But how could creatures like dinosaurs survive in a region that experienced months without sunlight? Some modern studies analyzing bone microstructure, particularly growth rates and vascular density, suggest that many dinosaurs may have had an intermediate metabolism, perhaps even approaching that of warm-blooded animals. In addition, plant-eating species may have adapted to extreme seasonal light cycles by storing energy during the summer months, when vegetation flourished, and reducing activity during the long, dark winters. And within this harsh yet stable environment, giant creatures continue to thrive. This discovery fundamentally changes how we see Antarctica. It was not a barren land of death, but a complete ecosystem. One where life did not merely survive, but expanded to extraordinary scale. Yet the heavy footsteps were not the only sounds echoing through the ancient forest. Somewhere nearby, lighter and faster, something else was moving. And that is where the balance of survival begins to shift. And life is no longer only about endurance, but about the hunt. The evidence comes from the fossil remains of a remarkable species, Cryolophosaurus. This carnivorous dinosaur lived during the early Jurassic period, about 190 million years ago. Measuring roughly 6 to 7 meters in length and weighing an estimated 450 to 600 kilograms, it was not the largest predator to ever exist, but within the Antarctic environment of that time, it stood close to the top of the food chain. Its most distinctive feature was the curved crest on its head, resembling the hairstyle of Elvis Presley, earning it the nickname Elvisaurus. Some hypotheses suggest the crest played a role in species recognition, attracting mates, or even acting as a visual signal in the dim light of dense forests. Modern biological models suggest that a carnivore weighing around 500 kilograms would need to consume tens of kilograms of meat each week to sustain its metabolism. That means the surrounding ecosystem must have supported a large, stable, and continuous population of prey. So the question arises, did ancient Antarctica provide enough food? Evidence suggests that the food web in prehistoric Antarctica had developed into a fully functioning ecosystem. Yet Antarctica was not a stable environment throughout the entire year. Even though temperatures were far warmer than they are today, the region still experienced months of continuous darkness. What happened to predators during that time? When sunlight disappeared, plants stopped growing and the food chain was disrupted. Could large predators still survive? One hypothesis proposes that animals may have developed flexible metabolic strategies, allowing them to reduce activity during the dark season, similar to a partial state of hibernation. A second possibility is that the ecosystem did not completely shut down during those months of darkness. Some ancient plants may have tolerated low light and continued minimal biological activity, enough to support smaller herbivores. But are these explanations sufficient to account for the survival of large predators? Some scientists argue that biological density in Antarctica may have been far lower than in modern tropical forests. And it was precisely that pressure that shaped evolution. In a world where sunlight could vanish for months and food resources were never guaranteed, only the most adaptable organisms could endure. But the story does not end on land. Beyond the forests, another world existed, one where predators moved silently through the darkness of the ocean. Fossil evidence reveals the presence of marine reptiles, such as Mosasaurus, which averaged about 10 to 12 meters in length, with some individuals exceeding 14 meters. Their bodies were streamlined, their tails powerful, and their bite force is estimated to have reached thousands of newtons, enough to crush prey in a single strike. Alongside them were groups of plesiosaurs, with long necks and 4 paddle-like limbs that allowed sudden bursts of speed through the three-dimensional space of the water. Geochemical analysis of deep-sea sediments indicates that ocean surface temperatures at high latitudes during the Jurassic and Cretaceous periods were not cold at all. Estimates range between 15 to 20 degrees Celsius, at least 10 to 15 degrees Celsius warmer than modern polar seas. This suggests that Antarctica at that time was not covered in ice, but instead surrounded by a continuous belt of warm water. What could keep such an enormous body of water consistently warm? The answer lies in the way oceans store energy. Water has a high specific heat capacity, and when the polar regions enter months without sunlight, this stored heat is slowly released, preventing temperatures from dropping too drastically. These microscopic plants bloom in vast numbers, providing energy for the entire food chain. During the Cretaceous period, Earth experienced several large-scale marine oxygen depletion events known as oceanic anoxic events. During these periods, many marine species declined or went extinct on a global scale. When the continents were still connected within the supercontinent Gondwana, warm currents from equatorial regions could flow more easily toward the poles, carrying both heat and oxygen. This circulation kept the oceans in constant motion, an essential condition for sustaining large and complex life. During the Jurassic and Cretaceous periods, atmospheric carbon dioxide concentrations are estimated to have ranged between 2.5 and 5 times higher than present levels. Carbon dioxide absorbs infrared radiation emitted from Earth's surface, trapping heat in the atmosphere and preventing it from escaping into space. It is a simple physical mechanism, yet when amplified on a planetary scale, it can completely transform the climate. But if carbon dioxide were the only factor, would it have been enough to turn Antarctica into a forest? Another crucial factor was continental distribution. And during this time, Antarctica was still part of the supercontinent Gondwana and had not yet become fully isolated as it is today. As ice disappeared, the planet absorbed more heat, creating a reinforcing feedback loop. The warmer it became, the less ice remained, and the less ice remained, the warmer the planet grew. Geological evidence shows that although the overall climate of the Cretaceous was warm, it was not completely uniform. There were periods of rapid fluctuation when temperatures rose or fell within a span of several 100,000 years, a remarkably fast pace on the geological timescale. When carbon dioxide levels began to decline, the greenhouse effect weakened and more heat escaped into space. At the same time, the continents gradually drifted apart, especially as Antarctica began separating from South America and Australia. This led to the formation of circumpolar ocean currents around Antarctica, preventing warm equatorial waters from reaching the region. And within that environment, a paradox began to form. An element not directly related to temperature, yet one that profoundly influenced the entire ecosystem. That element was light, a world where temperatures could remain stable, but the light itself was extreme. This phenomenon originates from a factor that cannot be changed: the tilt of Earth's axis, about 23.5 degrees. At latitudes around 75 to 85 degrees south, the region of ancient Antarctica, the sun could remain above the horizon for roughly 4 to 5 months during summer, and conversely, it would not rise for a similar period during winter. If light is the fundamental driver of photosynthesis, how did plants survive through such prolonged darkness? Evidence from fossilized ancient wood reveals something unexpected. Many tree trunks discovered in Antarctica do not show the clear growth rings typical of modern temperate trees. To survive months without light, plants would need to store energy in the form of starch or other organic compounds within their tissues. Some studies of ancient gymnosperms suggest that they may have had a much greater capacity for energy storage than most modern trees. But if plant activity slowed or stopped for long periods, what would happen to the entire food chain above it? The ecosystem of ancient Antarctica likely did not operate according to the daily rhythm of day and night like most ecosystems on Earth, but instead followed a seasonal cycle. During the bright season, energy production would surge, plants would grow rapidly, biomass would increase dramatically, and abundant food would become available for herbivores. These animals, in turn, would store energy in the form of fat or muscle tissue, preparing for the dark season ahead. When darkness arrived, the entire ecosystem shifted into a state of energy conservation. Activity dropped to a minimum, and metabolic rates may have slowed. Some species may have limited their movement, while others depended almost entirely on stored energy reserves. In most modern ecosystems, temperature is usually considered the primary limiting factor. But in ancient Antarctica, temperatures remained relatively stable due to the warm climate, while light fluctuated to extreme levels. But could such a system truly remain stable? If the bright season became shorter, or if sunlight intensity declined because of atmospheric dust, volcanic eruptions, or changes in Earth's orbit, the accumulated energy might not be enough to sustain life through the dark season. In that case, the entire ecosystem could collapse within a single cycle. What would happen if this entire system were disrupted not only by changes in light, but by a global catastrophe? Because in Earth's history, there was a moment when sunlight was obscured. Temperatures shifted violently, and nearly 70% of life disappeared. And when that happened, Antarctica was no longer a forest. The first phenomenon recorded by science is one of the greatest events in Earth's history, the end Cretaceous extinction, approximately 66 million years ago. Fossil data show that around 75% of all species on Earth disappeared, including all non-avian dinosaurs and many large marine organisms. But what was the true cause? The strongest evidence comes from a thin sediment layer containing unusually high levels of iridium, an element rare on Earth's surface but common in meteorites. This led to the hypothesis of a massive asteroid impact estimated at 10 to 12 kilometers in diameter, forming the Chicxulub crater in what is now the Yucatan Peninsula. In an ecosystem dependent on light, like ancient Antarctica, when light vanished, photosynthesis stopped. Plants could no longer produce energy. Within weeks to months, the primary food supply was cut off. Herbivores began to starve, followed by the decline of predators. A food chain once in balance now collapsed from its very foundation. The oceans were also severely affected as temperatures dropped and light diminished. Phytoplankton declined sharply. This disrupted the entire marine food web. Fossil records indicate that about 70% of marine species vanished during this event, including many groups of large marine reptiles. Some studies suggest the impact was not the only factor. Prior to this, Earth had already undergone intense volcanic activity in the Deccan Traps, releasing massive amounts of carbon dioxide and sulfur dioxide into the atmosphere over hundreds of thousands of years. This may have made ecosystems more fragile before the asteroid struck. In other words, the collapse was not a single event, but the result of overlapping factors pushing the system beyond its limits. Evidence from sediment layers shows that Antarctic ecosystems did not disappear instantly, but weakened rapidly. Because this extinction event was not a complete ending, but the beginning of a greater transformation, a journey spanning millions of years in which Antarctica gradually lost its warmth, lost its life, and moved closer to the state we know today, a frozen continent. The first phenomenon scientists identified was a long-term shift in temperature on a geological scale. By about 50 to 34 million years ago, during the late Eocene, average global temperatures had dropped significantly from around 20 degrees Celsius to levels closer to those of the modern world. One of the most critical factors was the movement of continents, as the supercontinent Gondwana slowly broke apart and Antarctica became increasingly isolated from South America and Australia. This process reached a turning point around 34 million years ago, when the Drake Passage opened between South America and Antarctica. This event triggered a profound transformation, the formation of the Antarctic Circumpolar Current. It is the most powerful ocean current on Earth, with an estimated flow of about 100 to 150 million cubic meters of water per second. It acts like a vast wall of water, preventing warm equatorial currents from reaching Antarctica. When the circumpolar current formed, Antarctica became thermally isolated. Heat was no longer replenished, while energy continued to radiate into space. The result was a steady decline in regional temperatures, an irreversible process. At the same time, atmospheric carbon dioxide levels were decreasing. This decline may have been linked to increased silicate weathering, a process that removes carbon dioxide from the atmosphere, as well as the expansion of terrestrial plant life. Antarctica lies near the South Pole, the region that receives the least solar radiation on the planet. Once it lost its sources of heat from both ocean and atmosphere, it became the first region to cross the threshold into permanent freezing. Once ice began to form, the albedo effect, the reflectivity of ice, triggered a powerful feedback loop. Ice reflects up to 80 to 90% of sunlight, reducing heat absorption, causing temperatures to drop further, and allowing ice to expand even more. Around 34 million years ago, evidence shows that the first major ice sheets began forming on Antarctica. From that point on, the ice thickened over millions of years, eventually reaching an average thickness of about 1.9 kilometers today, with some regions exceeding 4 kilometers. Plant life gradually disappeared as temperatures fell and glacial cycles intensified. Animals were unable to adapt to the increasingly harsh environment. In the end, the entire forest ecosystem vanished, replaced by a land locked in permanent ice. The transformation of Antarctica was not a single event, but the cumulative result of geological and climatic processes, the separation of continents, the formation of a circumpolar current that isolated heat, and the weakening of the greenhouse effect. As these foundational factors shifted, the climate system crossed a critical threshold and underwent a complete reorganization. Antarctica, therefore, is not merely a geographic outcome, but direct evidence of the Earth's climate capacity for phase transitions when physical conditions are altered. The ancient forests did not truly disappear. They are preserved beneath the ice as a biological archive, retaining information about ecosystem structures, atmospheric composition, and the ability of life to adapt under extreme conditions. Earth's climate is a dynamic system, sensitive to cumulative changes, and capable of shifting into entirely different states once stability thresholds are exceeded. Antarctica today stands as a powerful reminder that gradual changes, when large enough, become irreversible. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.